Here's a figure showing the flow of energy throughout the US economy. This kind of figure is called a Sankey diagram. And in this diagram, the width of each of the lines shows you the amount of energy flowing from one box to another. On the left, we start with primary energy. So for example, the inputs of natural gas and coal. And you can instantly see some of the big important features of the economy. So for example, basically all coal goes to the electricity sector. Almost none is used anywhere else. Whereas gas goes all sorts of places. Some goes to electricity, some goes to residential uses, commercial uses, industrial uses, a range of places. Then you can see the electricity sector as the most important intermediate energy carrier. And then finally notice the four sectors into which we divide the economy on the right-hand side: residential, commercial, industrial, and transportation. So what we're going to do is go through a bunch of these individual pieces in detail and then return to this whole diagram so you can understand its complexity and compare it to similar diagrams for the world as a whole or for other economies. This is the flow diagram for coal, perhaps the most boring of these diagrams. It's boring because very little coal is stored or exported or imported in the US economy. Most of it is simply produced, and almost all is produced goes to the electricity sector. A little bit goes to industrial production for things like steel making. Perhaps one interesting thing to note about this diagram is that there are quite a few different kinds of coal. Coal is ranked according to its carbon content, which turns out to be related to how shiny it is when you have a look at it. So lignite is the lowest quality coal. It's really not that different from peat. And then you have subbituminous and bituminous. Those are the main coals that are really used to produce energy in, say, electricity or industrial processes where you just want the heat. Anthracite is particularly high-grade, high-carbon coal that's used for some purposes like steel making where you need pretty pure coal. The oil system is a bit more complicated. The two biggest inputs are domestically produced crude oil and imported crude oil. Another really important input is natural gas petroleum liquids. These are liquid fuels that come out of the natural gas system that get kind of moved over and counted as part of the oil liquid fuel system. All those things, including some imported material, flows into the refining system. Refineries essentially sort oil according to how chemically heavy it is, how many carbon atoms there are, what its vapor pressure is, but they also transform one kind into another. The refining system then produces a series of different refined products like motor gasoline, kerosene, which goes to aircraft, very heavy residual fuels, basically waste, that go to power long-distance shipping. Now look at what the outputs are of the oil system. Most of oil goes to transportation, about 2/3. But you also have a tiny bit of oil going to electric power and a significant amount going to industry. The US doesn't export any significant amount of crude oil, but it does export a significant amount of refined products, and also it imports some refined products. That's part of the global shuffling of different liquid petroleum products that is the integrated global refining industry. Natural gas is a much more complicated system. There are two big inputs, one from wells that are drilled just to produce natural gas, and others from wells that are drilled to produce oil, but also produce some natural gas. Then there's actually some removal of gas that wasn't natural gas, that counts in the original input, but doesn't count in the output. Then there are inputs and outputs of gas that are used for repressurizing gas wells to keep productivity up or keep productivity of oil wells up. There's also significant annual storage of natural gas. So you can see gas enter and leave from storage on different years. Finally, there's a thing that connects back to what we just said about oil, that part of the natural gas flow actually is natural gas petroleum liquids that then go back to the oil refining system. Finally, there's the gas products. Gas products go to a wide variety of final uses, sort of evenly split between electric power, industrial, and then residential and commercial. Electricity is an energy carrier. We don't mine it, but we make it, either using fuels like coal and gas, which are burned to produce electricity, or using solar, hydro, or wind, which directly produce electricity that feeds into the electric power system. Electricity consumption is roughly equally split between residential, commercial, and industrial, although residential is a little bit bigger. Note the surprising fact that electricity transmission and distribution, the flow of electricity through the wires from where it's generated to where it's finally used, is amazingly efficient. Only about 6% of electricity generated is lost in transmission and distribution losses. Next, electricity. The first thing to notice is that about 2/3 of the energy that flows in as coal, gas, or nuclear heat is wasted. Only a little more than 1/3 of that heat gets turned into electricity. Second, let's look at the amount of renewable energy produced. There's an interesting and important accounting trick or uncertainty here. Energy sources like solar photovoltaics or wind turbines or hydropower make electricity directly. There's no conversion from heat to electricity. So how should we count them? The most obvious thing is to count a gigajoule of electricity supplied by one of these direct-to-electricity renewables as equal to 1 gigajoule of primary energy. But that would make the contribution of, say, hydropower look less important than it really is. As you see in this picture, where half of the electricity is supplied by coal and half by hydropower, but the primary energy contribution from coal is 3 times as large. So most accounting for primary energy counts the primary energy contribution from these direct-to-electricity renewables, like hydro, solar, or wind, according to the amount of thermal energy they displace, as in this diagram, which describes the same story with respect to the actual generation of electricity, but now counts the primary energy contribution from that hydropower as being 3 times as important. There's no simple right answer, but most diagrams, like the ones from North Livermore or the US Energy Information Administration that we're showing you, these diagrams do typically use this factor of 3 accounting. One thing to bear in mind is that if the world makes a transition to use more and more of these direct electricity sources, this accounting scheme will look more and more silly, because then the primary energy will depend on the conversion efficiency of the relatively small amount of remaining coal or gas. The last big thing to notice about electricity is that the T&D, transmission and distribution losses, are very small. In the US, they're about 6%. That means that on average, the US electricity grid is 94% efficient in moving electricity from where it's produced through all the complex network of wires to the final places where it enters a home or business to be used.